Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Um, Today I will continue the basic electronic circuit. After we learn about the chapter 4, DC biasing BGT, today I will show you what is the field effect transistor or FET. Okay, this is some of subchapter of FET today, and the first one, I would like to show you what is the differences between BGT and FET. Currently, BGT is current control device. It's mean that BGT is current control device, and then FET is voltage control device. It means that if you remember that the BGT is like this one, so this is the base, this is the emitter, and then this is collector. We control the current here from collector to emitter or IC using the current in base or IB here. Okay, so this means that this is the current control device. But an FET, the symbol is like this one. So this is the gate, and the terminal is the gate, and then this is the drain, and this is the source. So the current flow from the drain to source, the control is not the current in the gate, but we control the current IDS by using the voltage in gate or VG. Okay, so this why the FET is voltage control device. And then the most important characteristic of FET is high impedance. And so if we look, I will show you the FET. FET is like this one. So we have three terminals here. This is the gate, and this is the source, and this is the drain here. And this is the insulator here. So this is the insulator, SiO2, silicon oxide. This is the insulator. And prevent the current flowing from the gate to the channel between the drain to source here. So if we want to if we want the current flow from drain to source, so it's maybe here is the channel here, and then this is the channel here, this is the channel. So the current can the carrier can flow, or the current can flow from drain to source. So in the gate we put the insulator here between the gate and the channel, so there is no current from the gate through the channel, and then only the voltage here. This is the VGA or the gate voltage. So the BGT has much higher sensitivity to change in the applied signal, because if we see there is no insulator here, so they control the current, collector current, using the base current. So the sensitivity is higher than FET. And then the typical AC voltage gain for BGT amplifier are great deal more than FET. So if you want to design the amplifier, and you would like to get a higher gain, higher voltage gain, so BGT is more appropriate than the FET, but the sensitivity is higher than the FET. So it's just an option. If you want to amplifier that the amplifier, high gain amplifier with lower sensitivity, maybe it's like a trade-off. You can choose the BGT, you will get the higher voltage gain, but the sensitivity is higher. But if you choose the FET, the voltage gain maybe is not higher, not as high as a BGT, but the sensitivity is lower. So you can choose this trade-off. And then FET is more temperature stable than the BGT, and the FET is usually smaller than BGT. So in IC design, in amplifier IC design, the FET is more popular to be used than the BGT. Okay, this is some differences between the BGT and the FET. And then we have three types of FET. The first one is JFET or junction FET. And then we have MOSFET, metal oxide semiconductor FET. And MOSFET have two kinds. The first one is depletion type and another one is enhancement type. And then the last one is MESFET, metal oxide semiconductor FET. Okay, so this is a three type of FET. I want you to looking for these differences between the JFET, MOSFET, and MESFET as a today assignment. So I actually I have the explanation here. I mean that in this PPT. But maybe I just skip the explanation and please you elaborate or you find the differences between three kind of FET here. Okay. Okay, so the JFET, the JFET is the structure of the JFET. We can see is this is the N-channel JFET. This means that the N-channel JFET has two p-type semiconductor and then one N-type semiconductor. And p-type semiconductor is a gate, and N-type is for drain and source here. This is the drain, and this is the source, and p-type for the gate. So it's like we can see the JFET, the working principle is like the water analogy like this one. So this is the source and this is the drain and this is the gate. You can imagine that if we want to, if we would like to the water flow in this mechanism, so we have to control the gate. So the water will flow. I mean that in the depth of the water will be smaller or bigger or larger, depend on how we can control the gate. Okay, so this is the analogy of the JFET. So we can see here, if we control the gate here, so the depletion region here between the p-type and p-type will be larger like this one. Okay, so I will show you like this one. So if we put the voltage between the gate to source here, you can see this is the positive voltage. So in p-type, if we put the positive voltage, so the hole in p-type will go in. I mean that it will not attract to the positive voltage, but is repel. Is like this one. So push to the another side like this one. So the hole will go like this one. If we put a positive voltage to the p-type, and then you can see between the p-type there's n-type here or electron. So the electron will recombine with the hole to create a depletion region. So you can see from this one, if the VGS is equal to 0 and VDS equal to some positive value, so there is a depletion region between the p-type, this one and this one. Okay, and the electron can move from the source to drain, or the current from drain to source will move also. Okay, and then if we put so this is the, if we put the VGS is equal to 0 and VDS is equal to 2, so we can see here this is the differences between this this point and this point is 0.5. This is 1 volt and this one is 1.5 volts. We can see that the depletion region will form in this if we put the VGS equal to 0 and the current can control, and we can make the depletion region maybe you can imagine that if we put more VGS here, so the depletion region will larger, will be larger, like, and then this one, if the depletion region in this side, in left side and in right side, is meet in the middle of the junction of in the middle of structure, so it's called it's pinch off. So we call it if we put like this one, oh, this one is pinch off, this one is pinch off. Okay, when the pinch off is happen, so the current is like in the saturation region, so the current is in saturation region, and saturation region is like this one. So this is the saturation region. The current will flow, but in the similar magnitude when we increase the VDS. Okay, if the pinch off happen, if and we increase the VDS, the current will stable. It will remain stable in that value. So this is the saturation region, and this is the ohmic region is before the pinch off. So the before the pinch off is mean that the depletion region in the left side and right side is not meet in the middle. So there is a channel between the left side of depletion region and right side depletion region. So if we increase the VDS like this one, increase the VDS until the some value, we call it the VP or the pinch off voltage. So the current will be go in saturation region. Whatever we increase the VDS, drain to source voltage, the current will be stable like this one. Okay. And then if we increase more the VDS, the pinch off will be broken, and then we call it breakdown region, and then the current will go. I mean that will larger and larger, like unlimited. So the device is like broken, so we cannot use that JFET anymore. Okay, so we have to very careful in this breakdown region. Okay, so this is the JFET, this is the N channel JFET, and this is the P channel JFET here. Okay, this is the N channel and this is the P channel. Okay, so the summary is the maximum current is defined as IDSS. IDSS is the ID saturation. So this is the ID saturation. Occurs when the VGS equal to 0 and VDS is larger or similar to the pinch off. It's shown in figure 6.15a, like this one. Okay, if forget and to source voltage VGS less than pinch off level, then like this one, so the VGS less than pinch off level, like a negative value of VGS. So the drain current is 0 as ID is equal to 0. And then for all level of VGS between the 0 to pinch off level, the current will be in ohmic region like C. So you can see from here. Okay, so this is the saturation region when the VGS is equal to 0 and VDS similar and larger than VP here. Okay, so this is the IDSS. So this is the IDSS. And then if we decrease the VGS like this one, okay, so if the VDS lower than VP, so this is the ohmic region, and then after the VDS similar to VP, so this is the saturation region. It's similar to the VGS is equal to -2. Okay. Okay, so here the equation of the if we compare the equation of BGT or IC current collector current is the function of the IB. It means that this is the constant beta and then this is the control variable. So we can see that the BGT is current control device, and then the JFET and the relationship between the ID and VGS is defined by Shockley equations. this is the ID. This is similar to the IC here, and then this is the constant, and this is the control variable. So we can see from here that this is the voltage control current. Okay, so from here we can see how to see the characteristic of JFET when VGS is equal to 0, ID is equal to IDSS, and when VGS is equal to VP, here, the ID is equal to 0. So the first one, the characteristic is like this one. So when VGS, this is the VGS here, and when VGS equal to 0 here, so ID is equal to IDSS. And then when VGS equal to VP here, for example, VP is equal to -4, so the ID is equal to 0. And then we have two point here, and we have to looking for another point to draw the characteristic of the device. Okay. The first one, okay, maybe I will put this one. Oh, so okay. You can see this mathematical equation, but I will jump to this one summary. When the VG is equal to 0, so ID is equal to IDSS. When VGS equal to VP, ID is 0 milliampere. And then when VGS is 0.3 VP, ID is IDSS per 2. And when VGS is 0.5 VP, the ID is IDSS per 4. So we can see from here, for example, we have VP is equal to -6. Okay, VP is equal to -6 here. And then the ID is 12 milliampere. So we can see when VGS equal to 0, ID is equal to IDSS. So we put 1 point here. And then when VGS equal to VP -6, ID is equal to 0, IDSS equal to 0. So this is 1. And then another, when we can see here, when VGS is 0.3 VP, VP is -6. So 0.3 VP is 0.3 dot 6 is -1.8. So the ID is IDSS per 2. IDSS per 2 is 6. So we can draw this point. Okay, so we can draw this point. This point is 0.3 VGS, and then this is IDSS per 2, and then this one is 1.5 VP, sorry, not VGS, VP. So we have the IDSS per 4. So IDSS is -3. So we can get this one. And then we can plot this one. Okay, so this is the characteristic device of the circuit. Okay, now this is another example. Sketch the transfer curve of P channel with the IDSS is equal to 4 and VP is equal to 3. So from here, we can, from this equation, we can put 2 points. The first one, when ID is equal to IDSS, the VGS equal to 0. So this one here, the first one. And another is when VGS equal to VP, 3 volt, ID is equal to 0. So this one. So this is the second point. And then we have to put 2 more points here. When VGS is VP per 2, or 1.5 here, okay, so the ID is equal to IDSS per 4. This is 1. So we have another point here. And then the last point, when ID is IDSS per 2 or 2 milliampere, so the VGS is 0.3 VP, like in this summary. So we can get another point here. So we make, so this is the device characteristic of the P channel FET, and this is the specification sheet of the JFET. You can see here, yeah, it's similar to the BGT, and then also the maximum rating. And yeah, you will learn about this JFET and specification sheet in the lab. Okay. Okay, I think this one, the first one of this class about the JFET. Thank you for the attention. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.